So until now, what we saw was data that was smaller, kind of well-behaved, where we were able to glean all of those insights very nicely within the given tools. What happens if your data is massive? So we're talking about millions of rows, several features, not all of them make sense, where you need to craft intelligible features out of the data that you're given. So the next demo talks about the use case where we have big data doing data prep and analytics at scale, then doing a visualization of the reduced data set and creating an interface for business users to see the insights, but also develop a collaboration between the data science teams and the business users. Talking about the project, this comes within the realm of using technology for good. We partnered with a nonprofit, Tipping Point, to look at citations data and evaluate the impact or the burden of those citations on different groups within the data provided. So we looked at it by car and we came across some very startling discoveries that I'll share with you in just a minute. So talking about the tools first, we have Spotfire Data Science. You can see I'm inside the workspace now. So this is what the look and feel of the workspace is. You can see it's very interactive. A lot of different team members can add their comments, add links to the file, and you can sort of trace almost a Slack-like interface for tracing file changes. And if I go to the work files itself, for any of these files, there's a list of activities that tells you what has happened, what are the changes, what are the kind of commits. So you can think of it very coarsely as almost code documentation and change list and commit list. From here, I can click on any one of the files and it's going to open that for me. So let's go in and look at the workflow. This is the workflow that we use for analysis. As you can see, it's a very nice UI-based tool. I can select operators from any of these categories, or I could go in and type something to look for the operators that I want. So XVDF or regression. And once I get that, it's just about dragging and dropping it and configuring it. So the data that we had available was several different tables. We had citations with zip code, we had business locations, location of parking spots, center lines and road information. And as you can imagine, that not only did we have to analyze these individually, but we also had to create a master list of what it looked like together and query all the different pieces together. So I have here several aggregations. Then after we're doing the aggregations, we're joining by it so that we're not creating duplicate rows. And then we're doing correlation analysis, we're doing regression analysis to see how the different variables basically relate with each other. I want to show you unpivot because this is my absolute favorite. When you exceed a certain data volume, the moment you go above a few thousand rows, if you try to do full joins or if you try to do unpivot in most tools, that would cause it to break. But over here, we're doing in-database analytics of big data. So you can have your data sources to be Spark, Hadoop, any kind of big data source. And then you're doing in-database, all of this. So to configure it, and all of that complexity is abstracted away from the user. So when you're working, you're not really thinking about the Spark job syntax that you have to run or the command syntax that you have to run. You're only thinking about the action that you have to take. So it's very easy. Just select the columns and specify how you want it to be saved you can give your output directory. This output directory is also going to be within your big data source so that you can now transfer it from one operator to the other operator. And you don't have to always rerun things from the source. You can just step run the next one. So a lot of these amazing built-in functionalities and optimizations have let us accurately and appropriately create summaries and stats and relations between the different tables that we have. So from here, now that we've looked at this entire pipeline of data join, cleaning, and aggregations, we're actually going to look at the result of it. Let's go in and see actual dashboard. And again, I accessed it from here. So if I just go in and do the Spotfire dashboard, it will open up. But it takes a little bit of time to load up because it's close to 3.9 million citations. And we have data about 1.3 million cars. So this data comes from the city of San Francisco for the year 2012 to 2017. As you saw, we queried with a number of other open data sources that were available. So for example, we took San Francisco government provided center lines. We took SF rent data and minimum wage change history data. So from there, for those of you who are not familiar with San Francisco, let's first just look at what the neighborhood looks like. So here, I've colored it by affordability. And this is still California affordability. So even the most affordable in San Francisco is probably not that affordable. So we start with the white regions. These have low density. There's a lot of parks in this region, sort of the adjacent South San Francisco region. And then we move up in color to the more expensive ones. And once you reach the downtown and the beach areas, the nice views around the Twin Peaks and all of that, it starts to get more expensive. So on top of this, I can actually show you the roads. And once we overlay it with the roads, you can see that the expensive areas follow the major roadways. So for example, this entire area is expensive. You've got a major roadway here. You've got a major freeway running in this direction. And this is the popular downtown street, but also a lot of internal BART and public transportation runs across these. So these tend to be a little bit more expensive. So our initial estimate was that in these downtown areas, we would have higher ticket amounts, higher number of tickets. Now that we know the geography a little bit, we overlaid it with the ticket data that we had. So now you're looking at the citations view. Every single point is an individual parking citation that has been given out. So it's colored by the amount. So you can see a lot of the citations fall within the 200 to 400 category, but you also have some really crazy expensive citations that go above 1,400, above 1,000 and so on. Now, you can see that this data is very dense. What I mean by that is that 2 different parking spots are 2 different points on this map. If I select only the lower end citations, so the $200 to $399, we can see that all of my data filtered by that. And we can see that zoning and location related citations are the most expensive in terms of average amount, followed by street cleaning, followed by plate and registration. And a lot of this density is around the areas that you would expect. A surprising thing that we saw was that a lot of the even expensive number of citations that were given out, they were given out to regular cars like Toyotas, Hondas, Ford. Even if I go to the slightly higher end of citations and select that, you can still see that the economy cars show up as being the highest citations within that category. This could happen simply because we have that many Toyotas and Hondas on the street, or maybe something more is going on. So we decided to look at it by car. On the left, we have the distribution of cars by age, and then we color-coded it to signify categories. The cars that are 10 years or younger, they're called new cars, and cars that are 20 years or older, they're called old cars, and then you've got the other categories. You can see that the patterns for tickets for all the cars are pretty similar. So for example, everybody tends to get more tickets on the weekend. Everybody tends to get the most tickets during lunchtime when they're probably, parking in a location they're not supposed to grab a quick lunch or something. Then we start to look at the proportion. So if you look at the total number of cars, about 6.3 are old cars percent, and 60% are new cars. When you look at the number of citations given out, that is pretty much the same proportion. But once we start to look at the amount, so for example, if I show you the amount of citation by type of car, it's close to 7% for old cars, and it reduces to 59% for new cars. And then if you look at the amount that is due, so payments that are totally or partially unpaid, you suddenly see it jump to a 12.2%. And for old cars, that's almost twice the original population in the data. So this was very alarming for us, because that means that the burden of the parking citation is heavier for people with old cars. This is significant because there is high negative correlation assumed between income and age of car. So if you're very well-to-do, you're probably not going to be driving a car that's more than 20 years old, with the exception of vintage cars that we filtered out when we were looking at plate numbers and so on. Next thing that we do is actually look at what is causing these numbers to rise. So we look at citations by violation. And within that, you can see that over here, every row is a violation type, and every column represents the car that is affected by that and the amount that's paying for it. So the white block mean all cars, the blue ones are new cars, and the orange ones are old cars. So if you look at average tickets for meter permit-related violations, you can see that for all cars, it's $81. The new cars, it's $81. But for old cars, it jumps to $89. This keeps happening across every category, average overall ticket amount. Average ticket for plates and registration is the worst, where you've got the entire population pays $110 on average. The new cars pay $105 on average, and the old cars pay $136 on average. So there's about 29.52% increase. Now, we calculated the living wage per hour in San Francisco over 2012 to 2017. And we actually saw how much of these amounts translate, how do they translate into minimum wage or the cost of living in San Francisco. So again, we start with the percent cars. You have 6.3% old cars and 60% new cars. If you look at percent number of citations, the percent citations that exceed 1 week of minimum wage pay, 7.9%, 8% of that go to old cars. And the number reduces for new cars from 60% to 54%. Similarly, if I look at citations that exceed 2 weeks of minimum wage pay, it's 8.6% for old cars. And the moment we look at how many citations are outstanding that exceed 2 weeks minimum wage pay, you see that 15% of all old cars are under that category. What this means is people are simply unable to pay the citations that are being charged. Not only the citations, but they're being charged late fees on top of it. A lot of these are citations that you can show a proof of correction and then go back and dispute your original citation. But if you're working 2 jobs, if you're working 3 jobs, you're not going to have 2 days of your schedule to go in and do that. This brings us to call of action. So the Tipping Point team, along with the TIBCO tech team at the time, the Alpine data team, wrote to the San Francisco Office of Financial Justice, and we showed them the data, and we showed them with examples what exactly was happening. So if I take the most common ticket that was given out, which is for street cleaning, it has a dollar amount of $68 initially. After 45 days, you have a $30 penalty. After 90 days, you have a $90 penalty. Total amount due at the end of 90 days is $188, which makes its interest rate per month effectively is 58.82%. Compare that to real estate. First of all, there's a grace period allowed to property owners, taxpayers, if they default in making the payments of 69 days, after which they have an interest rate of 10% per annum, which gives an effective rate of 0.83%. So the same city in 2 different scenarios has 2 different rates of penalty, and that's really impacting some of the population. So the good thing is that we've seen some movement from the FFMTA, and they're starting to bring in reforms starting March 1.